Okay, well, thank you to the 8 of you who came to class today. Um, and I don't know what I was expecting, but thank you guys for coming. Okay, I wanted to talk today about cross-validation and this idea of cross-validation and getting scores for like fitting different models and stuff. Okay, and let me see if I can do this. So the idea of cross-validation in model selection is the idea that you will take your, you have some data and you use your data to fit your model, right? And what's going on? So let's talk. So today is week 8, Wednesday, and we're talking cross validation. Okay, so here is, let's say you've got these data points here. Let's say we've got 6 data points, okay, and so what cross validation does is it says, you know what, if we just took our 6 data points and we fit a model, okay, this is our model, like, I don't know, would look something like this. Can I draw a line? I don't know. Okay, so this might be a linear regression model that we would fit to our 6 data points. Okay, and what cross validation says is, hang on, let's split our data into a subset, okay? Because we're using these 6 data points to train our model, meaning that we're using these 6 data points to figure out estimates of our slope and intercept, right? So we have 6 points in our training data, okay? And when we fit the model, we pick the slope and intercept, slope B1 and intercept B0, that minimize the sum of squared residuals. Okay, so maybe this is what we have. Now, cross-validation says, let's split our training data, in our case, 6 points, into like a train and validation set. Okay, and so we might say maybe we'll do 4 points over here and 2 points over here. Okay, and so if we take our data, okay, we might randomly say this point and this point will be our test data points. Okay, we just randomly pick, so maybe these ones are the test. Okay, and so now we fit a model based on the 4 data points in our training set. Okay, so fit a model. So this might be so if there's 6 data points and we say we're going to put 2 points in our validation set, this will end up being 3-fold cross validation. Okay, because we would form maybe 3 sets of 2. Okay, so this would be like 3-fold cross validation. And so we train on the 4 training points. And so we might say, okay, for these 4 data points, I'm going to try to find the line that minimizes the error of the 4 data points. I don't know what it's going to look like. Okay, so let's say, I don't know, does that look good? Maybe. Okay, so we do this, right? And then we say, okay, what's how much error do we have, right? And this actually, this is like worse than having no model. For these 2 data points, this is like worse than no model at all. Because no model means you would just predict the mean of these 2 data points, right? So for this fold, the fitted line is worse than having no model at all. Okay, because if you had no model, or we might call it an empty model, if you had no model, your prediction for the 2 test cases, or the 2 validation points, would just be the mean of those 2 points. Okay, so if you had no model, you would just predict, you'd say, all right, well, what's the mean of these 2 points? It's going to be right here. So for this point, we would predict here, and for this point, we would predict here, and the amount of error we have between our prediction and our test cases is only this much, right? But according to the model that we fit on the other 4 data points, the amount of error we have is the difference between our line, our data point, and what the line says it should be, right? So this is the residual, and this is a residual, okay? And so we can see that this red line that we fit is actually worse than having no predictor. Does that kind of make sense? So anyway, this says, well, maybe this is not a good model, okay? Okay, so if we use the red line to make predictions, we have big residuals, okay? The vertical blue lines, okay? They're much bigger than the residuals of just using the mean. Does that make sense there? Okay, but then, but that's not the only case, right? So another set, okay, if we just randomly pick 2 points, might be these 2, okay? And so we would try to fit our regression line based on these 4 data points. I don't know what it would look like. So you fit a regression line just on the 4 other data points, and you get something like this. Okay, I don't know. Does that seem reasonable? Okay, maybe, right? All right, and so anyway, you say, okay, well, let's look at. So then let me also just kind of plot like no model, right? So in green. Green would be no no model, which just means use the mean as our quote unquote prediction. Right? So here we would just use the mean of these two validation points, and so the no model would be halfway through. I don't know, something like this, maybe? Does that look halfway through? Okay, and so here we see our fitted line on the 4 points does a little bit better than having no model, because with no model, our regression is, our residual is the error between our prediction and the actual data point. Okay, so it goes from there to there. This is our residual for no model or an empty model. And then over here, the residual is a little bit smaller, okay? Because the red line gets a tiny bit closer to the prediction, okay? So, so our data points, you know, the red line does a little bit better. Okay, it predicts a value that is closer to the actual value than the mean of the validation cases. Okay, so you use 4 out of the 6 to train your model, and you get this almost prediction line, this red prediction line with a slight slope. Okay, and you just compare that versus having no model at all. Okay, and no model at all means you just predict the mean for everything. Okay. Yeah, question.
Why was it 3 folds? Like in my head, it would be 6 choose 2 folds.
Okay, it's we just call it K-fold cross-validation, and K just means take your thing and split it up into, in our case, 3 equal chunks. Okay.
Oh.
All right. Or you can say, with 6-fold, you can go 6-fold, 3-fold, or 2-fold, and you can do like 5-fold, and the computer will have to figure out how to assign the 5th points or 6th points and stuff. But in general, you just say like, if you have like 500 data points, you might do like 5-fold cross-validation, and that means you split the data into 5 chunks. You hold out one of the chunks as a validation set, and then the other 4 you use to train, and then you kind of cycle through. So here, we had 6 data points in our original data set. We're going to hold 2 of them out for validation. We use the other 4 to train. Okay, and we get this line. Okay, in this case, and then we go to the next set, and these 2. And then so for the last set, the last 2 points that we haven't used, these would be in our validation set, and we use the other points to train our data, right? And so in this case, we train our data based on this, and we get something, I don't know, that looks like this, all right? And then again, now we get probably performance worse than having no model, because having no model, we would just predict the same value for just the mean of the 2 validation cases, right? So we have, so these are the residuals. Well, I don't know. How big is the residual over here? Over here versus over here. Yeah, I think our squared residuals here is much bigger. Yeah. Versus this. I'm just making up squares here. But so and when we do cross-validation here, we're actually going to get a very low score. We're actually going to get a negative, okay? Because what you do is you're going to compare the performance of these kind of cross-validated models. And what this tells us is that, you know, our fitting a linear regression line might not, you know, outperform just like the mean or something, okay? But this allows us, this gives us a metric to compare different models, okay? We can say like, well, how does our thing perform when we fit different types of things, okay? So when you do k-fold cross-validation, okay, so if this is your training data, okay, so fourfold says split the data into 4, you know, equal or almost equal chunks, equal-ish chunks, right? And then you're going to fit 4 different models, okay? You're going to have, you're going to use, you're going to train on 1, 2, and 3, and you validate on 4. So, okay, validate is, you know, find a, you know, get a score of, you know, how much better is the model you trained versus no model, right? And then on the second one, you would use 1, 2, 4, and you validate against the third, and you get a score. And then over here, you train on 1, 3, and 4. And then lastly, you train on 2, 3, 4, and you validate against set 1. Okay, so you take each of these chunks and you train on the different sets, and then you compare it versus having no model. Because the idea is you don't want to overfit your data, right? And so if you overfit your data, you know, you might be making predictions that look good in your training set, but when you expose it to data that was not part of your training set, a validation set, you realize, oh, it's making bad predictions. Okay, and so that's what cross-validation does. And there's a few tools in in Python that that help us do this. Okay, so let me. I just kind of coded this up, so there's not a whole lot of commentary. So I'll be adding commentary as we go along. Okay, so anyway. We'll start by importing NumPy, Pandas, Matplotlib, and then from scikit-learn, what I'm going to do is I'm going to just compare fitting a linear regression and then polynomial regression for a quadratic and a cubic fit on some data here, okay? And then I've got model selection here as a way for cross-validation. So cross-validation is a model selection tool. So I'm going to say import linear model, import pre-processing, and model selection, okay? The data, I've got to upload this data here, but, or you can just follow along. The data is this data set called iron slag, and I forget exactly what the stuff looks like, or what the stuff represents. But when you create a plot, this is the relationship between, you know, some kind of chemical thing and some kind of magnetic thing, and this is the scatter plot we have, okay? And so, you know, is there a linear relationship, a quadratic relationship, a cubic relationship? I mean, there might be other relationships or whatever, but we're just going to test out those 3 things versus each other, okay? And so in order to get it to work in scikit-learn, you've got to use you got to give it a matrix, okay? And so here we just have one variable, the chemical, to be our predictor, okay? So I'm going to use chemical. So what I've done is I've done iron.chemical.values. So iron.chemical.values will give me, if I didn't run reshape, would pull out there's 53 points and would just pull out the one-dimensional array, okay? But scikit-learn requires that it be in a two-dimensional array, okay? sklearn requires our predictor variables to be in a two-dimensional array, okay? And then so I say reshape it, reshape it to have one column, okay? The -1 in reshape, do you guys know what the -1 means? Okay, the -1 is, so what I'm gonna end up having is I want 53 rows in one column, okay? What the -1 says is I'm too lazy to figure out how many rows I need, okay? So I'm saying just make sure you have one column, and NumPy, you figure out how many rows I need, okay? That's what the -1 says, okay? So the -1 in reshape means I don't want to figure out all the necessary dimensions, okay? I want one column, and NumPy, you figure out how many rows I need. Okay, so that's what you can do. Okay, so because in R you can specify a matrix and just say like number of columns is 1 or number of rows is this, and it'll figure out the rest. NumPy has something similar, except you say -1. I don't want to figure this dimension out. Okay, -1 just says I don't want to figure this dimension out. You figure it out. Okay, you can't specify, like if you're going to make like a three-dimensional thing. You can only have one -1, okay? All right, so anyway, and then y is iron magnetic, and then, you know, y dot shape is single dimensional, okay? All right, so here we will fit a linear model between x and y, okay? So to do that, we're going to, from scikit-learn linear model, we're going to call linear model.linear regression, and then we say linear fit x and y, and then linear.score is 0.5372. This is basically your r-squared value. Okay, linear.score is the r-squared value, okay, and it represents kind of the reduction in residuals between the mean squared error and the mean squared model or mean squared regression, okay? So it's kind of how much error is reduced from no model, okay, which is basically it's equal to the variance or MSE. So if you think of your ANOVA table, okay, and you've got your model, like the regression coefficient, and you've got your residual thing. In your ANOVA table, you've got sum of squares, residuals, and then you divide by n-1, and that's going to give you your MSE, right? So how much error is reduced from no model, your MSE, versus having the regression model, okay? And so, you know, our r-squared value is around 0.54. Let me see. can I do, I'm just np.core iron.chemical.values and iron.magnetic.values. Is it correlation? NP correlation core coef. And then core coef, let's get 0.1, and then if I square that, okay, so it's the correlation coefficient squared is 0.53722, and that ends up giving us our R score, right? So it's our R scored value. Okay, and so anyway, we fit the model, right? We have linear.fit, and then and I can say, you know what, I want to make some predictions. Okay, so I'm going to say we're going to create a matrix X. Okay, and it's going to be the values 10 through 33 or 10 through 32, because that's kind of the range of values that I have here. And then I'm going to make predictions for each of these things. So I use linear-model.predict, or linear.predict, which is the name of my model. So model.predict, I plug in my X matrix here. And then I'm going to create a scatter plot, and then I'm going to plot the line for the predictions here. Okay, and when we do this, this is what we have. Okay, this is our cross-validation tool. Oops. Okay, and so here, shuffle split says take the data, shuffle them, and create 5 different splits. Okay, so here, shuffle split says mix the data, or I'll say shuffle the data, and split it into 5 equal parts, right? And then from there, I can do ask for cross-val score, and it's going to basically figure out this score, which is the R-squared coefficient, which I talked about, for using a linear model on the data X and Y, and do the splits according to cross-validation, according to CV. Okay, so we're going to do we do this, and it gives me, these are the scores, negative 0.008, negative is never a good sign, okay, and then we have 0.49, 0.756, 0.65, and 0.412. So we want to know how good are we doing, all right? And the average of all of these things is 0.4609. Okay, I just kind of want to show you where these scores are coming from, and that's where I was spending a bunch of time trying to do this. Okay, so what I can do is I've created this object called CV. CV is a shuffle split object, and you can say do shuffle split on X. And what this does is it says, okay, I've looked at your data X, which is my matrix of 53 rows and 1 column, and what it will do is it creates an iterable, and each iteration will return a train and test index. Okay, so I can then subset my X data using the training index, and I create TX and TY. So these are going to be the training cases of X, and the training cases of Y will be TX and TY. Okay, I'm going to create a new linear regression model. All right, so here, maybe I'll comment all of these things. Okay, So create a subset of the data using the training cases in cross-validation, okay? And here we initialize and fit a new linear regression model, okay? Fit only on the training cases, okay? Now we create a subset using the for the test cases. So all I've done is I've subset my original x and y using the test indices. Okay, and then plot the training data in blue and test cases in green. All right, and then we'll also plot the prediction line, the fitted prediction line, based on the training data. You know what I should also do? I'll say, I'm going to do, how do I do this? Plot, I guess, numpy.mean test y. And we'll plot this one in, is there light green? I think. Plot the mean of the test cases for to show what having no model looks like. Okay, and then this will be the score of having no model, which is just the variance of the test data. And this is kind of the, not the score, but this is the MSE, and then this is mean squares regression, and then the score is the kind of proportion of reduction by having regression. Ah, shoot. X and Y must have the same first dimension but have shapes 23 and 1. Oh yeah. How do I do this? Plot this, and I need, how do I create a, what's a repeat in NumPy? NumPy repeat values in array. It's np.repeat. Okay. np.repeat test y on length x predict. Okay. So this is our first case, okay, and so the light blue dots, those are our training sets. So the red line is trained on these light blue dots here, okay, and then we see, okay, how does it perform on these test cases, these green dots, okay, and so if we had no model for the green dots, we would have just predicted the, I don't know, what do you call it? The mean of these things, right? And so when we look at this, okay, for this data, the mean was much better than the red line. The red line, we've got a huge residual, but the mean was actually much better. You know, this one, the red line is much better versus the thing, okay? And when we look at, when we compare the two, all right, we look at, all right, what is the kind of the average residual from the green line, which is basically the variance of y, Okay, that's the mean squared error. And then if we, for the mean squared regression is the actual data point minus the predicted data point squared, right? So that's the squared residual, okay? And it's the sum of squared residuals divided by how many cases we have. Okay, so that's kind of like the average average squared residual that we have. Okay, and then the reduction is the mean squared error minus the mean squared reduction, and in this case, the mean squared error is 15.71. And I'm sorry, the mean squared regression. The mean squared regression is actually higher. Okay, and so if we do MSE minus MSR and divide by the original MSE, we get a negative value. Okay, we get negative 0.008649. Okay, and that's where this value comes from, negative 0.008649. Okay, and then we look at, so we did, how many folds do we do? We did 4-fold. No, we did 5-fold cross-validation. Okay, and then so for the next data set, all right, we trained it on the light blue cases. These are, and we're saying, how well does this red line fit on the green cases? No model, we would just predict the light green line for everybody, okay? And so when we do that, there's a reduction, right? So the light green line says our mean squared error, our variance, our MSE, is 48.734. If we use the red line to make predictions, our mean squared error is only 24.696, okay? And so that's a reduction of 0.4932, okay? And so our, so we get 0.4932, right? And so we can look through all 5 folds. This one seems to do a very good job, right? This one does a very good job. And so we have a reduction of around 75%. This one does pretty good also. We have a reduction of around 65%. And this one does okay, reduction of 0.412. And so the average of these things ends up being our cross-validation, average cross-validation score is around 46%, 0.46. Okay. And then so what we can do is we can do the same thing, and I didn't bother making the graphs for every single, for all of these things, but the idea is the same. So here, I'm going to do a polynomial fit, okay? And so you have pre-processing polynomial features creates a polynomial based on x, right? So what this does is it takes, I do poly 2, so I want a squared polynomial, and I apply it to x, and what this does here is if I just print poly x, we see it takes our original values, okay, which were 1 and 24, and then it creates 24 squared is 576. Okay, so it polynomial poly 2 creates a column of to the 0 power, to the first power, and to the squared power. Okay, and so it's kind of hard to read, but we have 1, 16, 256, 1, 24, and 576. Okay, and you can do this, you know, for single values and squared things. Okay, so that's poly x. All right, and then we're just going to do fit a linear model. Okay, because I have a column for the ones, I'm going to say fit intercept equals false. Okay, and we fit it, and we ask for our score, and we get 59%, and we can just see, you know, let's see what this looks like. Okay, and so our fit looks like that. Okay. These are, if we do the different things, these are our different scores, and we get a cross-validation score of 0.5035. here we can do a cubic fit, okay? And I guess just in your head you have to picture that the computer is doing something similar here, except instead of fitting a straight red line on the light blue dots, it's fitting a quadratic line to the light blue dots, okay? And then it's comparing how well does that thing do versus having no model. I guess I can try writing the code up really quick, okay? All right, and so we can do a cubic fit, all right? And we say, all right, what if I fit a cubic model for all the things, okay? Then my average cross-validation score actually goes down to 0.455, okay? So when we compare the three models, okay, the average cross-validation for the linear model was 0.46, 46% reduction in mean squared residuals. For the quadratic, we have a 0.503, and for the cubic, 0.455, okay? So the cubic fit, you know, if we look at it, it seems, you know, maybe it reduces the error the most, okay? On the full data set is 0.598, but when you do cross-validation, its cross-validation scores is actually worse than the linear regression model, okay? Here, let me see. Maybe if I always say don't do this, but I'm going to copy and paste, and we'll just try to, let me, whoops. So what I actually have to do is I have to do a pre-process poly 2. Poly tx will be on tx, and then fit linear regression on poly tx, and then plt scatter on the training x, training y, test x, test y, that's fine. X predict on, I gotta do poly 2 dot fit underscore transform on x predict. I think that's what I need. Let me just see if this looks right. Oh, didn't like that. Oh, okay. And then, oh yeah, CLN predict. Are those numbers lining up? Negative 0.0103. Yeah, 0.5538. Yeah. Okay. So anyway, this is what it looks like. So here we're training the curved red line on the light blue dots, and we're saying how well does it predict the green dots? Okay. And in this case, it doesn't do that great of a job. In this case, it does a better job. This one looks like it's doing a great job. Okay, and so we can see, you know, the curved red lines for each of these things are, you know, they look different, okay? And again, I'm going to break my rule of saying don't copy and paste, and I'm going to copy and paste, and then here I want to use, I think I want to use poly 3. Let me see, and I'll call this poly 3 tx, poly 3. Poly 3 tx, poly 3, and poly 3. I think that's what I want. Okay, so 0.0175, 0.512. Yeah. Okay. So fitting a cubic fit, we get this, and you know, because we're fitting it on the light blue, we get, you know, a cubic fit that looks like this. Over here, we're training it on the light blue, so we get a cubic fit that looks like this. And over here we get a cubic fit that looks like this, and a cubic fit that looks like this. Okay, and so we can, you know, we can see how the bias variance trade-off works here, right? So when you have a model that's a lot more flexible, the kinds of lines that you end up fitting look quite different. And depending on the data that's coming in, right, you might be able to fit your training data quite well, but you're overfitting. So here, okay, we fit the light blue dots, okay, and so we get this red curve, but we can see, you know what, that's actually not doing a good job of fitting the test cases, okay? And so we're doing cross-validation. We're splitting up our data into kind of training and validation sets. We fit a different model and we score them appropriately, okay? And so here, I went through the bother of like manually splitting up the data and whatever, okay? Scikit-learn makes it very easy, and you just say model selection, cross-validation score, and it calculates all those things for you, just right there. And here I just kind of showed you where these calculations are coming from, so you can be confident that the thing is actually working. But you probably don't have to bother showing all of these different cross-validation plots. But I don't know. For me, it was helpful. It's helpful in knowing how these score numbers are coming from, right? Because when you see a negative score, it's like, really? Is it truly? How can I get a negative score? But when you look at it, and you go, oh yeah. If I look at how my red line performs versus having no model, where I'm just predicting the mean for everything, we can see that the red line might not be actually any better. Okay, well anyway, thank you guys for coming to class today, and I hope you guys have a wonderful Thanksgiving holiday and break, and we'll see you guys on Monday.